Thanks for having me at Multicore 10 this year. It's a great privilege to hear all the different talks going on, and hopefully this aligns with a lot of the conversations that have been started through the questions. It's really interesting to hear about the cloud, OpenAcc support, and all the different GPU enablement. And what I want to show you and introduce to you today, if you haven't heard of it, is the Rockum software stack, which is our open and portable GPU compute solution. And we'll go through a bunch of different parts of it, and we'll have a chance to answer questions at the very end. So just a quick cautionary statement since we're currently in our quiet period. And just to give a bit of background first on the hardware, AMD was sort of outside of the HPC space for a few years. The EPYC processor has really gained traction in this environment. And we see with the win of El Capitan and the previous one, the Frontier supercomputers, the combination of the CPU and the GPU is really leading that HPC environment for the exascale era. These are huge machines. They're coming over the next couple of years. But what that also brought is lots of questions on how to enable a software programming environment that would work across many different architectures. So if you look at the history of the supercomputers, some of them say the last 10 years, there's been single GPU, multi-GPU, and that ratio changes from generation to generation with the number of CPU sockets to GPUs. And each of those programming environments is complex to get the best performance out of that without having to really rewrite your code. And I still don't think there's a silver bullet or some magic solution that will solve this today, but we're getting closer, and I'll walk through some of the components that we think helps that process. So what is Rockum? It's our open source software platform. So everything we're contributing here is open source, right from the device driver, the compilers, libraries, programming models, the integration with our different frameworks, as well as the programmer and system tools for monitoring the system. We see that very important for different environments. Some customers don't really care. Other customers really want to get into the nuts and bolts and do optimizations themselves, as well as have a way to either control their kernel and their whole operating system. And so over the last few years, we've been building up this ecosystem. Rockum first started around 2015 and 2016. And at 2018 at Supercomputing, we launched our 2.0 platform, which had a pretty solid foundation of being able to do GPU compute problems. Over the 2019, we spent more effort on Rockum 3.0, focused on machine learning and building out support for that infrastructure, those libraries. And over the past year, with the focus now on Frontier, for the delivery for next year, we're emphasizing the libraries for HPC. So a lot of the infrastructure required as well to go along with that. So supporting interconnects as well as deployment systems. And this wouldn't be possible without a whole collection of partners in the ecosystem. And it's really neat to see the embracing of that happening. So there are a couple interesting comments today about how to run your code. Docker support is quite common, but it is painful in some supercomputer or data center environments where you don't have the privileges needed to run certain containers. Singularity helps solve some of those problems. So if you have a Docker container, you can actually run Singularity. And with both of those, we have enabled the GPU support. So it's capable to run those containers that are built for the AMD hardware. Slurm is another common workload manager. We have the GPU enablement in there as well, so you can submit your job and dedicate how many GPUs you want to run at the time. And then Kubernetes is another way of doing orchestration of container jobs or splitting out into multiple pods. It's very common in the machine learning space. There's a device plugin required to enable that for the GPU, and that's supported there as well. And then we look at Trace Compass and some of the other ones I'll talk about coming up with the debugger and profiler. But I want to spend a little bit of time talking about TensorFlow and PyTorch. The talk this morning mentioned the value of doing machine learning in integration with the weather codes. So if you have implemented something today on using other hardware, the AMD implementation, both TensorFlow and PyTorch, is fully upstream. So that means you can just recompile your application and target the AMD version of those frameworks. So one other key component is part of the exascale computing project. And this is for really looking at the tools to manage thousands of GPUs in a data center to go along with the programming models and then optimizing for applications. So in the machine intelligence space, in weather, probably the image recognition would be the most sort of part that would be the interesting, but it's definitely being used across the industry as a workflow in terms of inserting processing before you do your heavy jobs, or in the post-processing to analyze the results. And if we look at some of the machine learning models supported with the AMD hardware, image classification, ResNext 101 might be quite an interesting one, as seeing high performance there. As well as we go forward in time, the reinforcement learning or generative models could be very useful in the weather environment, looking at prediction from past events. So I want to talk a little bit about the compiler stack and some of the options available to compile your applications and develop for the GPUs. And first up is HIP. That's our heterogeneous interface for portability. And in a couple slides, I'll go through a bit more detail about how we have support for both NVIDIA and AMD hardware. But really, this is a compiler that's based on LLVM. It compiles the standard C++ code, and we have directive or very specific APIs for HIP that give you device implementations of those libraries. Then we also have OpenMP support. So AOMP is, again, an LLVM-based implementation. And these compilers will be merged into one tree because we're trying to push everything we can upstream into LLVM. And then we still support OpenCL for those applications that have been traditionally using that in the industry. On the Fortran side, it's very important to have support here. The AOMP compiler has that support for Flang. And we've also spent a bunch of time building out a new project called HipFort. And I don't have the link for the GitHub here, but I invite you to go just search for it on our Rockum GitHub page. And what it allows you to do is to use our C libraries with standard ISO C binding. And we've done all the sort of hard work of wrapping that for you. So in your Fortran code, you just have to include the mod files, the modules, and then you can call the libraries as needed. So things like BLAS support or other low-level functionality. And that's, again, fully open source, and people can contribute to that project by adding other libraries as needed. The advantage of that is that you can use then your standard Fortran compiler and get the GPU offload support. And then OpenACC is another common offload model for GPUs. We're done a lot of work with Mentor they have sort of built the back end of GCC to support the AMD ISA. So our interface to the hardware, we published that. They've implemented that and upstreamed a lot of the work. In May, they released their compiler that's built on that implementation, and it supports OpenACC version 2.6. And then it'll be a new release coming out again in November. And then over the next couple of years, it's a public announcement now that Oak Ridge has helped fund them to support this GCC work for OpenACC and OpenMP to support both the hardware that Oak Ridge has purchased, so both NVIDIA and AMD. And then there is a side project in LLVM. I've seen a little bit of work on that where they've taken OpenACC code and moved it or converted it to OpenMP, and then you can use your OpenMP compiler. So along with the compiler, it's useful to have a debugger that's unified with the CPU. And we've done this with ROCGDB. So this integrates into the standard GDB command line interface. And we're working with the partners to create the graphical environments that people are accustomed to using. The advantage here is that you can step through your code from your CPU threads, see what's running on your GPU, and what's happening in the registers in both devices, as well as your memory settings. And then similar, we've done that with the profiler and tracer. So here it's more based on PAPI as the combined method to synchronize events. So that way you can run your code. It gets timestamped. You can peruse it through something even like a Chrome browser because it exports it as a JSON file and see what components are taking the most amount of time and then optimize that work. And we do this with a lot of the partnership in the academic industry. So we released versions of these, and basically every month we try to do a new Rockum release. It's been a fairly rapid development process. And so as time goes on, the code base gets more and more functionality as well as more stable. And with all of this work, we're trying to upstream it as much as possible so that your standard tools just have native support. So let's talk a little bit about HIP and how this works and supporting both libraries. And the key advantage of doing it this way is that you end up with one application that can support multiple versions of hardware without having to maintain separate branches. And so if you have a CUDA-based application, you can Hypophy it, and I'll show that coming up in a couple slides. And with that, you end up with a bunch of code that interfaces to both the AMD version and the NVIDIA version, and then you just compile for your specific target. And this slide shows a little bit more detail on how that works. It's really just through an interface that's an API, and then includes the appropriate headers, and actually uses the NVIDIA tools to compile the NVIDIA path. So it's fairly straightforward. It's easy to do, and one of the key things of why this works is because at the very low level, the implementation of a kernel is basically identical. So as you go through these different layers, you see that's the same, but as you port from CUDA to HIP, most of it is just a simple string replacement. With the exception in this diagram, or this bit of code, it shows the difference between launching the kernel. On the NVIDIA side is the triple Chevron, and the HIP is an API call. The latest release of Rockum actually supports the triple Chevron methodology as well. And so with this common sort of API, we've also built similar libraries. And so if at a library level, there's an abstraction layer that can then make it even easier for you to integrate it into your application. So if you're writing a new application, you can just write to the HIP APIs and then have support for both NVIDIA and AMD. And as part of that, there's, we're building out this whole set of comparable libraries to the ones that you would expect in using different HPC applications. So BLAS library is very important, FFTs, sparse libraries and solvers for linear algebra. There's the thrust algorithms, low-level primitives, and then the deep learning solver library is MI-Open. That's our name, and that's included in a lot of the TensorFlow and PyTorch code. Then we have random number support. The eigen port is actually fully upstream, so that's used quite often for the linear algebra. And then Nickel is the communication primitives library, and RICL, so Radeon Communication Collectives library, is this similar functionality as that. And if you look at some of the hardware architectures as the GPUs connect to each other, or you want to do multi-node support, these type of libraries come into play. So in terms of how to Hypophy code, we have two sets of methodologies. One's the Hypophy Perl, and the other one's Hypophy Clang. So Perl is really just a search and replace technique. It does a quick scan of the project. So you basically just point it at the directory with all your code, and it scans and replaces the code with the HIP implementations. The Hypophy Clang actually uses the compiler front end, does a bit more robust translation of the code, and generates warnings and assistance if there's something that it can't quite understand. So you get a bit higher quality translation, but you do need to have the compiler tools to do that, where the Perl methodology is just quick and easy. And so a quick example of this is some work we did with NAG. It's the CUDA library, so it's hard to say, but it's CUDA on CUDA, and it supports many of the different libraries, or uses many different libraries, as well as has a lot of hand-tuned kernels. And when we first started scoping the project, they estimated this was going to be a single developer, 6 months of effort. And actually within 15 days, they had an executable up and running the test code on our hardware. And the main reason of that was the supported libraries, so the equivalent libraries that I went through before, as well as the Hypophy code it was quite easy to translate that code, but a lot of the effort was actually in the make and build environment. And that's what we've seen with other examples as well. Sometimes a port will take 10 minutes to actually convert the GPU-based code, but the rest of the day to work out the build environment. And so usually the next question is, well, is there an overhead? And this is actually a great blog article by Fluid Numerics, who published some work that they did with their self-fluids workload, and on their kernel that they show, they take the same code, they Hypophy it, and then they run it again on the same NVIDIA hardware. And so this shows that there's really no performance degradation on NVIDIA hardware. And so that's a great thing. So there's really no loss in value in going this methodology. So another highlight in the ecosystem is just where people are taking HIP and implementing it into their own code base. So Grid Tools is a great example for the weather environment. You've probably heard of it. It uses the stencil operations, and they have native HIP support in their functionality. And we've seen very great performance on our hardware with that environment. Magma is another library that's used in a lot of HPC codes. Ginkgo is popular for linear algebra. Of course, there's FFTs and other high performance and accelerated matrix math libraries that are being ported to support both the AMD hardware through the HIP interface. So one other thing I want to mention here, and I didn't call it out specifically on the slide, is the concept of domain-specific languages. There was a talk yesterday about Cyclone and how that's driving some of that work. So that's another whole methodology where the underlying component of those languages worry about the details of the hardware, like supporting OpenMP or OpenACC or HIP or CUDA, and those are abstracted from the scientists trying to do their problem. We've seen a couple other examples in other industries, like DeVito is a good one, where they're using OpenMP and OpenACC to do that same process. They write their code in Python and then actually generate the low-level interfaces for the hardware through a dynamic process and then compile it. So I can see that being one of the industry trends going forward. It's a little bit more motion towards domain-specific languages. So hopefully that was a quick introduction to Rockum. I invite you to check out some of the resources that are listed here. I believe all these slides will be posted. There's some training videos and other tutorials. And if you have any more questions or comments, please get back to me. That'd be great. And thank you so much for your time today. Okay, so jumping into the question. Will AOMP support Fortran type bound procedures for GPU offload? Support Fortran type bound procedures. I don't know off the top of my head. I will have to look that up. Sorry about that. The second question is unified memory handled by AMD GPUs? Is there any hardware mechanisms, or does HIP manage data movement in software? So today it's all software managed. That's a good way to say it. I can't quite talk publicly about what the future will hold. But yes, the unified memory is handled by the software stack.